The importance of relative humidity. When one is dealing with the internal conditions in a building, it's effectively relative humidity that is the major factor. Why? Because it is this that potentially leads to health problems, especially related to dust mites, mould, bacteria, viruses and so forth. It is what we could call loosely a damp environment. Mould growth can occur on certain moisture-sensitive materials, such as leather, cloths, wood, and they do this by maintenance of relative humidities simply in excess of 80%. High relative humidities also lead to an increase in other items which have been implicated in health problems such as dust mites, bacteria and viruses. And of course, surface temperatures of walls and other cold areas, such as behind cupboards and so forth, will inevitably be several degrees lower than the room temperature. Thus, the relative humidity in the boundary layer of air against such surfaces will then be in excess of 5 to 15% higher, occasionally even greater. And of course, a cold environment will lead to higher relative humidities under what we would regard as normal airborne atmospheric moisture levels. These will then add to a risk of mould growth, plus the other agents such as dust mites, which can occur in such situations. If we look at properties, we found that analysis of a number of what we could loosely call non-problem houses in living areas showed that during the colder months of the year, around 60% RH as an average, and that's important, and less are achieved. Therefore, a practical method of making an assessment is to make an assumption. That is, to assume the internal occupied areas are comfortable and a constant 20 degrees. If, after this assumption, the relative humidity is, on average, much above 60%, then ventilation is needed. If, after this assumption, on average, it drops below 60%, then increase in heating is required. However, you need to assess this over a period of time. It's important to note that in a cold environment, by raising the temperature, we can reduce the risk of mould, dust mite, and so developments, as this will lower the relative humidity. And this diagram illustrates this, as we've illustrated it previously. 14 degrees at 80% relative humidity, we would have a risk of mould. However, if we can increase the heat to 20 degrees, the relative humidity drops to 50% and the mould risk is gone. This was a case study, and it was cold in the house. The actual temperatures were between 12 and 18 degrees. So we recalculated these conditions, and this now assumes the temperature was raised and maintained at 20 degrees, and we finish up with the graph we can see. But even doing this, raising the heating to 20 degrees, the relative humidity would still remain high. You can see this on the left side of the graph. It's averaging 70 roughly. But what's happened on the right hand side of the graph? There has been a drop in external moisture levels, and this has caused a drop in internal levels of atmospheric moisture, and hence a drop in the relative humidity. So if we look at these figures overall, especially the first part on the left, more ventilation is needed to reduce the relative humidity, as well as some possible slight better heating. We noted in the previous property the internal relative humidity dropped during the colder weather, solely due to the external water vapour levels dropping. This clearly shows the importance of the effect of external environments. And we saw this in a previous presentation. In a warm period, we've got internally generated water and externally generated moisture. That is the total moisture. Add those two together. Whereas in a cold period, we actually lose a proportion of the external moisture. There's less moisture in the atmosphere when it's cold than when it's warm. And thus, for a constant temperature, the relative humidity in the property would fall. And that is why it is essential to monitor external conditions, because this can significantly influence the internal relative humidity. Therefore, we really need to do this over a period of a minimum of 2 weeks, as long as 4 weeks, if possible, even longer. There's another case study. This was a kitchen. The lady was getting mould in the cupboards, and this was the result that we had from monitoring the kitchen and the cupboard temperatures and relative humidity. Note the very high relative humidity in the cupboard. Also note at the bottom, the green line, how low the temperature was in the cupboard, about 10 degrees lower than it was in the kitchen. So what we did, we recalculated these figures, assuming a constant 20 degrees in the kitchen and in the cupboard. So when converted to 20 degrees, the relative humidity in the cupboard and the kitchen are similar. We can see that on the graph. The high relative humidity in the cupboard was solely due to very low temperatures, and it was nothing to do with dampness in the rear wall. We can also compare the vapour pressures in this case. In this case, we are comparing internal with internal. And again, we can see that the vapour pressures are very, very similar. So we have the same amount of water vapour in the air, in the kitchen and in the cupboard. So again, there is no extraneous source of water being added to the cupboard. The mould was simply due to the very high relative humidity due to the very low temperatures in the cupboard. It should also be considered that different materials vary in their ability to transmit heat. For example, dense materials, glass, steel and so forth, transmit heat well, whereas the more open materials such as polystyrene, fiberboard, etc. do not conduct heat well. And it's why these materials make good insulation, because they can maintain a good temperature differential between the warm and the cold. Again, looking at a property, the coldest areas are usually on north-facing walls, possibly east-facing. These walls are most likely to be at risk to surface condensation. On west to southwest walls, dampness could be water penetration, especially through cavity fill. In most parts of the country, it is the southwest walls that are subject to the weather and the wind. And of course, thermal bridging can occur in areas such as metal window frames, concrete lintels and doors, etc. However, it is very important to appreciate the surface temperature of walls and other cold areas behind cupboards and other restrictions, wardrobes, will inevitably be several degrees lower than the room temperature, and then the relative humidity in the boundary layer of air against such surfaces will be in excess of 5 to 15% higher, sometimes as much as 25% or more. And a cold environment, as we've seen previously, will almost certainly lead to higher relative humidities under what one would regard as normal, reasonable airborne atmospheric moisture levels. When we get these factors, they will lead to a risk of mould growth, and indeed the other agents we've mentioned occurring in such conditions. So to summarise, the relative humidity will be higher in a cold internal environment than a warm one under the same conditions of occupation. Relative humidity is important in that where it remains suitably high, it can result in mould growth and proliferation of other microorganisms. Relative humidity against external walls is higher in the boundary layer of air, that is, air in direct contact with the wall, due to such walls being colder than the internal air.